Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on General Physics 2, we want to start to talk about the electric potential, one of the ideas used in electrical engineering, and is derivable from the electric fields. So before we get started, please consider subscribing as well as liking the video, and also please check the description below for the notes in this entire discussion. So let's just jump into the definition of the electric potential difference. So what's this electric potential difference? So the easiest way for you to describe such things is by actually thinking of the energy first. So let me just remind you that the change in internal energy is pretty much the negative of the work, or the negative of the integral of F ds. And so if I have, let's just state a point charge, and this point charge is moved through an electric field, we would know that the force in this charged object will be Q times the electric field. So we could just actually substitute this value inside this work. So we would obtain the negative Q with the integral of the E vector dot ds vector. So from this, we do see that we could actually develop certain ideas. Is that the delta U over Q is something which you call as the negative integral of the E vector ds vector. And just to note that if you remember that internal energy is a state variable, that means that this value here should also be a state variable, which means that you could only just give it a certain variable and you could know its entire system. So we'll just call that to be the voltage itself, or the change in voltage, because we are dealing with the change of potential energy. So this is the definition of the change in voltage, or the electric potential difference. So this electric potential difference pretty much tells you that if you multiply this value by the charge, you would obtain the potential energy of the process itself. So a unit of this value is something which you call as the volt. And this unit of volt is pretty much just the joules per coulomb. So it's pretty much the same thing but with a different name. And something very useful to use when you are dealing with micro-sized objects is the usage of a certain unit called the electronvolt. So this is pretty much the energy you need to move a point charge from a change of 1 volt. So that's the definition of the electronvolt, and the number itself is 1.6 times 10 to the power of negative 19 joules. So this is the conversion factor for you to use when you are swapping out between the electronvolt as well as the joules. And anyways, this value here is pretty much just the electric charge itself. So here is an interesting question for me to develop. If I have this delta V to be equal to the negative integral of E vector, and I would just call this as dr vector, just for convenience, we do see that if you actually take a very weird path that is not always the same as the electric field, you do see that you could see that the value itself will be changing, including the angle itself, which might influence its cosine theta. So the way for you to actually compute this integral is by doing a line integral. So this idea will later be discussed further when you deal with calculus itself. But in here, I won't fully discuss it as far as I can. So let's start to try to calculate the the potential difference. Calculate the potential difference. So one of the easiest systems for you to analyze is the point charge itself. So if I have this positive charge here, the question is, what's the voltage if I move from one point to another? Let's state into that certain direction. So there are multiple ways for you to view this. One of the ways is by only observing its symmetry as well, because you would know that the voltage here should be the same all around. But another way for you to do this is to just actually to do the integral itself straight away. So let's just assume that we are just heading out in this r vector, which is pretty much pointing outwards, and we'll just compute the object when it travels from this point A towards point B. So the change in voltage is pretty much the negative integral from position A to position B. And what's the E vector? The electric field will be kq over r squared, and it will be multiplied by the dr. And technically there's this r hat as well as this r vector here, but if you actually analyze the path itself, the r vector is just pointing in the same direction as the r hat. So if you do the dot product itself, this will just only obtain the dr itself. So it's pretty much very simple for you to compute its integral. So it's the negative integral of rb over ra of the kq over r squared dr. So we would obtain this to be kq over r. And this is and you would compute this from rb towards ra. So this would be kq over rb minus kq over ra. So you do observe here that in general that the voltage itself should be kq over rb or kq over ra. And if you actually try to define where the zero is, because what we are computing is just the change in potential difference, that means that we could just set any single point as our reference point. In this case, I will choose at the point at infinity here to be 0. So if you actually do the computations again, but instead from a towards infinity, you could get the value to be kq over r, which makes sense even if you plug in infinity into it. So this is pretty much in general what the voltage is. And that's how you would normally define the voltage itself. So we have already discussed about this potential difference or the potential itself. So what about if I give you a certain system in which it has all of these particles with different charges? So the idea of voltage is that it also obeys the superposition principle, because it is derived from the electric field, which is also governed by the superposition principle. So therefore I could just write the voltage here to be the sum of the kq over r with each of the i's. And you could actually extend this further into the continuous range. So you could compute the voltage to be the integral of kq over r. Well, technically it's dq. So just by using this formula itself, you could obtain lots of voltages with any different kind of shapes, as long as you can do the integral, of course. So after we have already started to talk about the voltage itself, we can start to give an idea that you could actually plot these potential differences and also its relation to the electric field. Difference and the electric field. So let's just give you an idea of this. So pretty much this voltage is that it is a value from negative infinity towards infinity, and it is just one value. So what if instead of me only showing you what the number is on a on a specific point. Instead you could just think of it as there is this hill that is being governed by each of these charged particles. So the way for you to do this is by actually thinking of the idea from calculus itself, or multivariable calculus, in which you introduce something called the level set. And in here, instead of us calling it as the level set, we will just call this as the equipotential. So the equipotential itself means that this is a surface or a set of lines which has the same voltage. So for example, if I take a point charge with positive here, I could draw certain lines here to show its potential. And let's just state this is 1 volt, 2 volt, 3 volt. No, technically it's not true. It's 3 volt, 2 volt, 1 volt, and etc. So you might have already looked at this from the map perspective. So if you have already experience with looking at a map, you do know that the more lines it is the more steeper this hill is. And that's the same idea when you deal with equipotential, is that you'd have this much more steeper hill. And another thing to remember is that the voltage is the negative integral of E vector dr vector. And if you actually try to multiply both sides by the certain operator, which you call as the nabla. So the nabla itself is defined as the partial over partial x, partial over partial y, and partial over partial z. Or pretty much, it's like the gradient. So this nabla here, or the del, can be multiplied by the voltage to obtain something like this. So it's the nabla times the voltage. It is equal to negative nabla integral E vector dr. And here's something interesting when you're dealing with the nabla vector itself. The nabla vector itself, when you multiply it by this negative integral of the r vector, it will pretty much cancel each other out, since they are both inverse functions of each other, or inverse operators. So you would obtain the negative E vector in here. So you do see here that this is E vector, which equals to the negative nabla V. So what you see is that the electric field is pretty much defined as the gradient of the voltage, but in the negative side. So that's pretty much the way for you to define the electric field in terms of voltage, or vice versa. And this idea gives you a much more clearer idea in terms of the physics itself. So if you have, let's say, a particle with positive charge, so let me just draw something like this. So if I have a positive charge, and this thing here is the plot of the voltage, you would see that there is this certain gradient here. So this gradient here will pretty much define how this particle will move. So pretty much it is as if that there is gravity going down, or pretty much it wants to go in a lower energy state. So this positive charge wants to go downwards into this direction. And for negative charges, it works in the opposite way. It wants to go into a higher voltage. So you could actually try to figure this out by using the definition of the E vector and try to find its relation with the voltage itself. So the way for you to actually use this nabla is that you just need to put in the v inside. So it's negative partial v over partial x, that's in the x component, and do the same thing in every single component. And this is pretty much the definition of the gradient itself. Lastly, I want to talk about charged conductors itself. So last time I have already discussed about conductors and also charged conductors, in which you figure out that the electric field inside of this object has to be zero. It has to be zero for a conductor. And there would be electric fields at the surface, in which the value is about sigma over 2 epsilon 0. But so if you actually try to translate this into voltage, the idea is, since inside the E vector is 0, this would equal to the negative nabla times V, or the gradient of V, negative gradient of V. You would know that this would mean that the V itself must be constant. Otherwise, that in here, there would be a certain value. So we know that inside of this conductor, it has to have a constant V. And this works for almost any single conductor. So even if I attach it with a very long wire, this voltage and this voltage has to be the same. So pretty much you could actually define what is electrostatic equilibrium by only taking the definition from this charged conductor. So electrostatic equilibrium literally means that conductors are equipotentials. Equipotential. No, equipotential. So that's the definition of electrostatic equilibrium. So before I end the video, I want to discuss a little bit about voltage itself as a whole and how to use it in terms of electrical engineering. So normally you would have like a battery, and there will be a resistor or something else, and then there could also be capacitors as well as inductors. But in here, we'll just discuss a little bit about voltage as well as the resistor, even though I wouldn't really fully discuss the whole thing about resistance as well as current. But let's state that this battery itself here has a potential difference of 5 volts. So you would know that the change in this voltage has to be 5 volts. And these wires here are conductors, meaning that they are pretty much in equipotential equilibrium. No, sorry, it's on electrostatic equilibrium, or pretty much it is a equipotential. So that means that this entire wire here, let me just use a different color. This entire wire here resembles 5 volts. Well, if you actually take the ground node to be 0. So what does it mean if you take a ground node? It pretty much means that you are setting this value to be 0, because the only thing that you use in terms of potential energy, no, sorry, for electric potential is the change in the voltage. So it is okay if I define a certain point to be 0 as long as it is distributed among other voltages as well. So it has to be normalized with that value as well. So if I state this point to be 0, that means that with this change of voltage, this top side should be 5 volts. And at the bottom here, it should all be 0 volts. So I can discuss a little bit more about circuits. And one thing that I want to discuss a little bit is about parallel circuits. So if I have 5 volts and then in here that's ground, the reason why at this point as well as in this point is also 5 volts is because this entire system here is in a equipotential, and same idea here. So that's why the potential difference on this first resistor as well as the second resistor is also 5 volts. which means that you could actually do certain ideas with this to determine the resistance. And this will later be useful when we'll later discuss a little bit more about capacitors. But this will all be done in a future video. So with all of that, I want to say thank you very much for watching this video, and also please consider subscribing as well as liking the video, and also please share this to the people who really need to know and understand physics much more better. So thank you very much, and I will see you on the next video.